the next family of problems we'll discuss are known as the traveling salesman problems. So these are motivated by, say you're a salesman who has to try to do sales in many cities. Well, you'd like to travel to each one of those cities exactly once. And it has applications beyond that. You'd also like to end up at the city you started at, because you probably live there. These types of problems have many applications. Just say you're a person who wants to go pick up 5 of your friends and go somewhere. Well, then go back to your house, let's say. That remains consistent. Finding 5 of your friends and then going somewhere else, that's a different problem. That's actually next week. But say you want to go to 5 of your friends and then bring them back to your place. Well, that's the same type of problem. You want to go to 5 places and wind up at the place you started. These are all known as traveling salesman problems. Traveling salesman problem. And the traveling salesman problem, the goal is to find the trip of minimum cost that a salesman can make in order to visit the cities in a sales territory once and only once, starting and ending in the same city. So I'll write that down. Find the trip of minimum cost. I'll abbreviate min, of minimum cost, and the cost can be anything. It could be distance, it can be, I don't know, say you're in a taxi and it's a taxi fare or something, or it can be miles, or it can be profit, or it can be revenue. There are a lot of costs. It could be whatever cost is most important to you in the given graph. So find the trip of minimum cost that a salesman can make in order to visit each city exactly once. While starting and ending in the same city. So right here, this is just a fancy way of saying, given a graph, find a minimum weight Hamiltonian cycle. Minimum weight means we're trying to minimize the cost. Hamiltonian cycle, we're visiting each city exactly once. And here, well, we already discussed one way of doing this. You can list out all of the possible ways and find their cost. If you have 10 cities, you would need, what, 9 factorial over 2. So whatever that number is, that's a large number. So it might be useful to have another way of solving them. And we'll discuss 2 different algorithms that we can use. So let's first do the one known as the nearest neighbor algorithm. Nearest neighbor algorithm. So here's how this algorithm works. You start at the home city. Then you visit the city that's closest. Now what does that mean, city that's closest? Well, city that's closest in terms of what your costs are. So whichever in the graph would have the lowest weight, that's what you go to next. And then you keep doing that until you hit every city. So let's see how that works. Yeah, okay, I'll write out the formal statement. The 2 algorithms we'll discuss, I find their formal statements much more complicated than actually doing them. So these words might seem like they're describing a lot, but hopefully when we go through the example, it becomes clear what we're doing. So nearest neighbor algorithm. Start from home city. Then you visit nearest city. And what we mean by nearest is in terms of cost. Well, then you keep doing that. Well, I'll say, then visit the next nearest city that you haven't been to. And then keep doing this until you have the entire cycle. Because remember, the cycle you want to end at the same place. So once you keep doing this, you're going to hit every city, and once you hit every vertex, you just go back to the original. Remember, we have complete graphs, so we can do that. And so I'll just say, keep going until all vertices, I guess we're saying cities, all cities are hit, then return home. It's called nearest neighbor because you start somewhere and you go to the closest place. I need another piece of chalk because this one is too small. I don't normally just throw my garbage on the floor, but I'll pick that up in a moment. So we'll do two examples. We'll do the first example we did with Cleveland or Cleveland turned into Detroit, and Chicago and Minneapolis, St. Louis. And then we'll do an example with 5 cities. And then we'll do the same thing with a second algorithm. So let's draw the first graph. So example. Apply the nearest neighbor algorithm to this. Apply nearest neighbor algorithm to each of these. I'll draw that bigger. I don't have to draw that small. Let's see if I can leave that there without knocking it over next time I walk by. So here we had Chicago, St. Louis, Detroit, Minneapolis, and we had costs. This was 774, 541, 300, 349, 562, 42. I can't tell if that's a 3 or a 5. 5. So we'll apply the nearest neighbor algorithm. And remember, in this example, we're starting and ending in Chicago. Well, the nearest neighbor algorithm says to go to the place that's closest. In this case, these are distances, so closest actually makes sense. Find the place with the lowest cost. Well, we can go there, 349, there, 300, or there, 425. The lowest is 300. That's what the nearest neighbor algorithm says. Go to the closest one. Well, from St. Louis, you could go to Detroit, 541. You could go to Minneapolis, 562. You could go to Chicago, 300, but you actually can't because you're already there. So that is the lowest one, but you can't go there since you were there. So all you have are these two choices, 541, 562. Well, 541 smaller, that's where you're going next. Now, once we chose that, the rest of our path is decided because this can't go back to Chicago, can't go back to St. Louis, so now you have to go down here to Minneapolis and then back to Chicago. So applying the nearest neighbor algorithm gives this total travel distance. Well, it gives this cycle, which has this total travel distance. 2,040 miles. You'll remember from when we did it by brute force, there were actually two better choices. This was actually the worst choice. So right here, this nearest neighbor algorithm gave us this. This nearest neighbor algorithm doesn't necessarily give the best choice, obviously. There were the other two choices from the previous video. Let's look at another example. Apply the nearest neighbor algorithm. This is also in the book. To to this. Consider this graph. We'll do 5 vertices. With 5 vertices, your numbers, well, the organization could get a little rough with all the lines and numbers going all over the place. So we have these 5 cities. Let's complete the graph. That looks awful. Down here, it looks awful. So there's the completed graph. Let's label these nodes, vertices, or nodes, same thing. Now let's give these costs. 600, 700, 400, 800, 500. Now these other ones, you have to be a little careful with your labeling so you don't wind up labeling them wrong. Right here, 750. That's E to C, 750. Right here, this one will be 850. This one will be 550. This one will be 650. This one will be 950. And that's all of them. We have 10 edges, we have 10 numbers. Apply the nearest neighbor algorithm. We're going to, for this one, starting at A. And then, well, let's start at A. So you start at A. You want to go to the place that's closest in terms of these costs. Well, look at the 4 things going out of A. This is the complete graph on 5 vertices, so we have 4 things coming out of A. 4 things coming out of each vertex. 700, 550, 650, 600. 550 is the smallest. Next, we start at D and we go somewhere. Well, where can we go? We can go 400, 850, or 800. So we go 400. From E, where can we go? Well, we can't go back to A because we still haven't gone to B or C. We can go only to B, which is 950, or C, which is 750. So that brings us back to C. Well, we hit A, B, or we hit A, D, E, C. So now from C, there's only one place you can go. You can't go back to D, over to E, back to A. You have to go up to B. And then we need to complete the cycle by going back to A. So starting at A gives us this cycle. It gives us A, D, E, C, B, A. And what's the cost? The nearest neighbor algorithm is going to give us a cost. What's the cost? Well, A to D 550 plus D to E 400. I apologize if these numbers aren't showing up nicely. This graph is in the textbook in Chapter 2, Section 3. It's probably the first or second example. I think it's the first. But bear in mind in that this 650 and the 950 are very poorly placed. The 650 goes A to C, the 950 goes B to E. The rest of that example, if this doesn't, I hope this shows up. Next week, I do plan on getting some colored chalk, so I won't have to do everything in just white chalk. This would be useful to have different colors, possibly on video. So A to D 550, D to E 400, E to C 750, C to B is 500, and B to A is 600. And these numbers all add up to 2,800, which I did not just do in my head, because I have it right on this page. This one wouldn't be too hard to do in the head, because you can get rid of these 50s. These two make 13, 17, and 11 makes 28. But I did have that written down. Now, one question you might ask is, what happens if you start at a different vertex? Well, this would be a good thing for you to check. What happens if you start at vertex B? Well, I'll give you the answer. If you start at vertex B, apply this algorithm, you will get a cost. I won't tell you the path. It's in the book, I think. Well, it is. I won't tell you the path, but it would be a very good thing for you to verify. So it might be a good idea to pause. You start at B, you get a path that has cost 3,050. You start at C, you get a path that costs 2,800. You start at C, you actually get the same cycle as you do in A. So it would be a good idea with this diagram to see if you could verify those. C, I'm pretty sure, is not in the book. But B is. Now let's look at this next algorithm. This next algorithm is called the sorted edges algorithm. Sorted edges algorithm. Sorted edges algorithm. Start by arranging edges in order of increasing cost. Then select an edge of least cost such that two conditions. It never requires that 3 edges meet at a vertex. It never closes a circular tour that does not include all vertices. Do this until you can't any more. I find that confusing, but I'll write that down and then we'll go through it with an example. Well, I find the phrasing confusing, I should say. Start by arranging edges in order of increasing cost. Then select an edge. So this selection, you start at the lowest cost. So this arranging assumes you start at the lowest cost when you go to this next step. Start an edge of least cost. It's written right in front of me. Of least cost such that these two conditions are satisfied. It never requires that three edges meet at a vertex. Two, it never closes a cycle that's smaller than the full thing. So it never closes a circular tour that does not include all vertices. A circular tour that does not contain all vertices. Continue until you're done. I find this phrasing quite complicated, especially with all these nevers and nots and conditions and all these things. I think this is much easier seen illustrated with an example. And we'll do those same two examples. We'll apply the sorted edges algorithm. Now, in this sorted edges algorithm, it doesn't assume you start anywhere like the nearest neighbor algorithm. So you think it might be better. There are cases where it's better. There are cases where it's not better than the nearest neighbor. But let's do those two with the sorted edges algorithm. Example, apply the sorted edges algorithm to each of these. I'm not going to label the vertices now. And what are these numbers? 425, 300, 774, 541, 562, and the other is 349. So apply the sorted edges. So the sorted edges just says list all these costs in order of increasing cost. This is probably the easiest place to make a mistake. You don't want to miss one of them. Right here there are 6 numbers, so we're going to have 6 numbers in our list. Excuse me. That says 541, 562, 774. And what we're going to do is just add these if we can. And that if we can is contained in those two conditions. And those two conditions are illustrated quite nicely with this example. This example from the textbook is a very good example for illustrating these things. We start here. We add that edge. Can we add that edge? Well, what happens if we add it? That doesn't screw anything up, so that's okay. Let's add the next edge. Can we? Well, what happens if we add this edge? Well, that still looks fine. We can still use those to create a cycle. What if we add this edge? 425. Well, that would be this one. What would happen if we did that? Well, what happens is it violates condition 1. But why does it violate condition 1? Why does that prevent us from getting a cycle that we want? Well, in order to visit these exactly once, you go there and you leave. You go there and you leave. Wait, maybe I should point at the camera while I'm doing that. You go there and then you leave. You can't go back. In other words, only 2 edges can leave each vertex in this cycle. Right here, we have 3 edges hitting a vertex. So we can't use that one. So I'm just going to cross that out. We can't use that one because we have 3 edges leading to a vertex. You need to travel somewhere and leave, and that's it. You can't go back. How about this next 541? Well, what happens if we include 541? Well, if we include 541, look at that. We're just going Chicago to St. Louis to Detroit to Chicago. We're not going to Minneapolis. And these people want to go to all four, and that includes Minneapolis. So if you throw this 541 in there, well, that violates what they're trying to do. So you can't throw 541. This is condition 2, because right here it contains a cycle that isn't big enough. Now that condition 2 wasn't written as contains a cycle that isn't big enough, because people who write math textbooks don't like to use the word big in that context. Big is too small of a word for people writing textbooks. But what happens if we add 562 to this? Well, that's okay. We can still make a cycle after that. And then what happens if we add 774? Well, that's okay, because it produced a cycle, but it produced the entire cycle. So this is what we got with the sorted edges algorithm. The sorted edges algorithm gave us that cycle. What does that add to? Well, that's these four numbers added together. 300. We can just add these all together like this. With these numbers, again, I would allow calculators. Add these all together, you get 1985, which is not optimal. I didn't add those together in my head. It's written down. This is not the optimal choice, but this is what this algorithm gave us. Not the worst choice. The nearest neighbor, I believe, did give us the worst choice. Now let's apply the sorted edges algorithm to the Pentagon. So we had that Pentagon, we had it completed as such. We had a bunch of weights thrown on this. 600, 950, 650, where am I? 650, 750, 700, 500, 550, 850, 400, 800. That's 10 numbers. 1, 2, 3, 7, 10. Yes. So now, oh, my phone is ringing. I apologize. I should take this. That's a convenient thing about online classes. I could take a call without interrupting class. So now we want to list these weights in increasing order. So here we have 10 numbers. We're going to want 10 numbers in our list. 400 is the smallest. 500, 550, 600, 650, 700, 750, 800, 850, 950. And that's all 10. 1, 2, 3, 4, 5, 10. 950, not 900. For some reason they skipped over that. Maybe that made it a better example. So what we do is we add edges starting at the top of that list. So you start at 400. Well, that's okay. That's not going to screw anything up. What if we then add 500? Well, where's 500? Over here. Well, we can still produce a cycle with that and that. 550. Can we add 550? Yeah, it looks like we can. What about 600? Where's 600? 600's up here. What happens if we add this? Well, that's still not creating one of those two problems. That did not create a cycle. That did not create a vertex with 3 edges going to it. None of them did so far. So we did these 4. These 4 are good. You could even put a check mark next to them if they're good. What about 650? That'd be amazing if that were good. If you added this 650, look what would happen. You would have that vertex having 3 paths leading to it. So that vertex up there, vertex A, would have 3 leading to it. So you can't add 650. What about 700? Where's 700? Right in front of me. If you added 700, that'd be this one, then you'd be making this triangle. You can't do that. We need a cycle to include all 5. That would be a cycle that includes only 3. What about 750? Well, 750 would be this one. That creates a cycle, but it creates a cycle that goes through all of the vertices. It doesn't produce a vertex with 3 things going into it. So that's okay. Any of these others that you add, you can't add. But you don't even need to consider them because you've hit all 5 vertices with a cycle at this point. So if we want the minimum, or if we want the cost associated with this, you add those 5 numbers together. They give you 2,800. Is that the? Yeah, that looks like the same one that we got starting at vertex A or vertex C. So that says apply, not apply. Apply. No, it doesn't even look like apply. So these 2 algorithms, definitely try them. They are the type that get much easier with practice. There are a couple examples. Well, there are some in the exercises, and there are some, well, there's one on the worksheet. So see how they go. Maybe I'll see if I can put a second on the worksheet. It's hard to find very good examples, even harder to make them. So see how that goes. And let me know if you have any questions.